Good morning. I'm Dr. Oliver. As part of the sustainability fair, this year we are introducing ourselves instead of having somebody do it. I guess it saves on personnel or something. So I am the chair of the biology department, and today I'm going to be giving you a talk entitled Hotter in the Water. This is about the effects of climate change and how that's going to be affected by and affect the ocean. How many of you have seen the ocean? All right, then you'll know what I'm talking about. So I am trained as a marine biologist. My specialty is in fish biology, ichthyology for those of you keeping score at home, and I will try to minimize the really technical fishy names. So when we talk about the oceans, they make up more than 70% of the Earth's surface. This planet really shouldn't be called Earth, it should be called water. And if you look at how much of our surface is covered by water to immense depths, you can imagine that there's a whole lot of the ocean that we don't know that much about. That has led to a number of assumptions about the ocean that are simply not true. In the past, the way humans largely solved the problem of stuff they didn't want anymore was to dump it in the ocean. The saying was, the solution to pollution is dilution. You dump it in the ocean and it goes away. Well, that turns out to not actually be true. If you look at how much water there is on the planet, and it is a finite resource, most of the water is in the oceans. More than 97% of all the water on the planet is in the ocean. Groundwater makes up 0.7%, ice at the poles and on glaciers about 2%, and then everything else is less than 0.05% of all the water. And that 0.05% is all of this: the lakes, the rivers, the soil, and the atmosphere. So we're talking about the vast majority of the planet is water in the oceans. And the oceans are really, really deep. 6,000 meters deep, you get to what's called the Hadal Zone, and down below that, darkness. We don't actually know everything that's down there. The deepest point of the ocean is the Marianas Trench. How deep is that? About 7 miles. Well, that's kind of hard to wrap your brain around. So here's an example. If you were in a boat above the Marianas Trench and took a cannonball and dropped it over the side of the boat, you could go make lunch, eat it, maybe watch an episode of your favorite TV show, because it's going to take over an hour for that cannonball to reach the bottom. That's deep. The shallow parts of the ocean are the parts we're more familiar with. Things like coral reefs with their wonderful diversity of fish. Yay, fish. But also you've got barrier reefs and lagoons. More fish. But there's a lot of stuff in this picture that you don't really notice. You don't necessarily notice the sponges or the corals or the various worms or all the other microbes that are growing there that are extremely important, which I'll talk about today. Mangrove forests. We don't have a lot of these in the United States, but if you go into Central and South America, any place where it's tropical or subtropical, you'll have mangrove forests. These are extremely important for habitat, once again, for fish. Largely juvenile fish go and live in and around the roots of these mangrove trees. But those mangrove forests also trap sediment, and they make islands that get bigger, which then allow more mangrove trees to grow. So they are a sustaining ecosystem. We, as a species, like to cut these down. Why? Because that's a great place to put a resort. It's not actually a bad place for a mangrove forest. These mangrove forests, particularly on the Gulf Coast of the United States, help to protect against storm surge from things like hurricanes. But we cut them down. And then what's left, the resort, doesn't protect against anything. And you can go and look at every hurricane that's hit recently. There are large stretches of areas that are devastated because the mangroves are gone, because we've cut them down. If you've ever been on Cape Cod, you know about salt marshes. And by the way, these little blue boxes are to catch the greenhead flies so they don't come eat you. If you've ever spent any time on the beaches of the Cape, you know that those don't work all that well. Salt marshes are also extremely important habitats. But this channel that you see through the salt marsh, this is in Sandwich, isn't supposed to be there. Those channels were cut there by people in order to drain the swamps We've heard that expression before. Doesn't work very well. Didn't work very well there. And so it's caused changes to the ecology of the salt marsh. And the salt marshes are really important because they help filter waste out of water. When you have nutrients running off of the land, they pass through the salt marshes. The plants take up a lot of the nutrients, largely nitrogen, and use it to make more planty goodness. So that stuff doesn't go out into the ocean. Because when nutrients go out into the ocean, it creates what are called dead zones. Huge blooms of algae and plankton, which then die and rot and use up all the oxygen. And you might have noticed that oxygen is important. It's important for fish, it's important for us. If you need an example, just hold your breath for the next 2 slides. You'll see what I mean. This is the distribution of salt marshes in black and mangrove forests in red around the world. Very, very important ecosystems, and look at how much of it is distributed through parts of the world that are developing. And developing often includes cutting down and taking down those kinds of ecological barriers. The consequences of that are pretty well known, and yet we continue to do it anyway. Because we're still doing that pollution is the solution to dilution thinking that, oh, so what if we cut down this mangrove forest? The answer is bad stuff, and it keeps happening. Out in the open ocean, you have large things like whales and sharks and large schools of fish. We don't eat those anymore. These have started eating us again. I can no longer say to my paranoid friends on the Cape, you know how long it's been since somebody has been killed by a shark on the Cape? Oh, this is like one of those, we are like 500 days without an accident in a factory. Like, okay, put it back to 0, we're starting over. But also, the oceans are home to large schools of fish that eat other fish. And those fish eat smaller fish, and those fish eat plankton. We need those fish for food. But we're taking too many of them at the top, harvesting too many, and we're chopping away the base of the oceanic food web. Those fish are becoming harder and harder and harder to find because of us. One of the big problems we face when we're talking about global warming, and I'm going to say that now, and then I'm going to stop saying it. We really ought not to call the problem we're facing global warming, because it's not just that things are getting warmer. And in fact, it's not even that things are going to get warmer everywhere. In some places, things might get colder. I prefer global climate change, because that's a better description. But the rate at which we're going right now, global climate destabilization is probably an even better description. That we are careening toward tipping points that once we pass them, things are going to change a lot all at once. And we know where those things are likely to happen, and we're still not doing anything about it. So one of the problems we face is what's called acidification. For a minute, I want you to imagine a world where you can put all the carbon dioxide you want in the atmosphere and it doesn't affect the temperature at all. We don't live in such a world, but let's imagine for a minute that we did. Then could we go, extra carbon dioxide? So what? Who cares? The answer is no. Even if putting carbon dioxide in the atmosphere doesn't make things warmer, which it does, it makes the oceans acidic. It's a simple chemical reaction. Carbon dioxide in the atmosphere mixes with water and forms carbonic acid, and as the name suggests, it will make the oceans more acidic. So what? Why do we care if the oceans are more acidic? Has anybody ever seen those nice aquaria that have tropical fish in them and the fake coral? On the bottom of those aquaria you have crushed coral, and the job of that crushed coral is to control the acidity. If the acidity gets too high in the tank, which will happen with fish, it dissolves the coral, and that coral buffers the change in acidity. So if water is acidic, it dissolves coral. Just like if your blood is too acidic, it dissolves your bones. Well, it's a good thing we don't do anything that will make our blood too acidic, except drinking acid stuff like Coke, Monster drinks, any of that stuff that's got phosphoric acid. If you drink enough of it, it acidifies your blood and starts to weaken your bones. Whew. How many of you ever heard of osteoporosis? That's that disease you get when you're old and your bones become brittle. The fastest growing disease among children in the United States is osteoporosis. Growing faster than diabetes is osteoporosis. How are kids getting osteoporosis? Drinking lots of soda. It acidifies their blood and prevents them from building solid bone and wears down the bone that they have. It's also lousy for your teeth. Well, ocean acidification is osteoporosis for coral. It causes the coral shell, which is just calcium carbonate, essentially the same stuff that's in your bones, to break down. So we're breaking that stuff down by acidifying the oceans. A quick discussion about what's special about water. Lots of things, and without going into a chemistry lecture as much as I'd like to, water is special for a number of reasons, particularly the way it forms chemical bonds. Because of the way it forms chemical bonds, it can absorb a huge amount of energy without changing its temperature. So it takes a lot of heat to change the temperature of water. But by the same token, it takes a lot for the water to give up that heat and to cool back down. So people say, well, if the planet's warming, that's fine, but the oceans aren't really getting any warmer, are they? Well, they are, but it's slow because water has such a high capacity to store heat. Part of the reason it's warmer in New England than you would expect for our how far north we are, and especially true in England itself, is the high heat capacity of water. So water crossing the Atlantic is the Gulf Stream, that's warm tropical water that went past the Cape, and it dumps a lot of that heat into Europe. If you were to shut that flow off, Europe would probably plunge into an ice age. We don't have to worry about that though, right? Global warming, right? We don't have to worry about that. You just wait. This power of water to store and transport heat is the major driver for world atmospheric circulation. In the tropics in particular, the air is heated by the sun, it expands and rises, eventually it condenses and forms rain, that's why you have rainforests there. But then it's distributed north and south by these convection currents carrying heat away from the equator. That's the global circulation pattern that drives our major wind patterns. And our major wind patterns largely dictate our weather. The major wind pattern that crosses the United States is called the jet stream. You've seen that. Everything kind of goes from the southwest to the northeast. And wind currents, winds, and water currents are named for the direction they come from. So a wind that blows from the southwest to the northeast is called a southwester. Unless you're a sailor, then it's a sou'wester. What happens when the wind pattern in New England changes, when it reverses, when it stops blowing to the northeast and starts blowing from the northeast? What's that? That's a nor'easter. And those are when we get the big storms bringing that stuff in off of the ocean to wreak havoc with, well, this whole summer and that really, really bad winter a couple of years ago. But that's all driven by these air circulation patterns. The wind blowing across the surface of the water moves the water, and that's what drives the major ocean circulation patterns. So this stuff is all tied together, and it is all powered and driven by the ability of water to store and transmit heat. Here are the prevailing wind patterns. The trades here, blowing from the east to the west in this band around the equator, and then the westerlies, blowing from the west, both from 30 to 60 north or from 30 to 60 south, and then the polar easterlies. Those are really predictable currents. In the age of sail, sailors knew when they could find and where they could find those winds, so they would plan their sailing routes accordingly. What's that? That's a hurricane. How do hurricanes get really big and powerful and strong? Water. Warm water is evaporating, rising up through the middle, dumping all of that heat from the ocean into the atmosphere, changing the pressure, making the winds blow harder, making the hurricane turn more, and sucking up more of that water. Why do hurricanes die once they cross land? Cut off their energy supply. What would happen if you made ocean surface temperatures hotter? You would make hurricanes stronger. And it's not just that the hurricanes are going to get stronger, although they seem to be doing that. It's that things that weren't hurricanes before are more likely to become hurricanes. It's not necessarily the case that every hurricane from now on will be a Category 5. But there are a lot of things that would have been tropical storms and tropical depressions before that are likely to tip over into hurricanes now because there's a better, more available source of heat than there was before. There's also this process called the conveyor belt. You move water through the surface up to the poles off of Europe where the water cools. Ice forms, and ice, even ice floating in the ocean, is just water. It excludes the salt. So if you needed water, you could just chip off a chunk of an iceberg and it would be fresh water. But the water that is left behind is colder, and it's saltier, and it sinks because it's more dense. And it makes its way to the bottom of the ocean, where it goes all the way around the world, and eventually it comes back up here. That means the water in the oceans is circulated around the entire globe from the surface to the bottom over very long periods of time. So part of the thing we're seeing now is that the surface temperatures are being warmed, and then that warmer water is being taken out of the surface to depth. So it takes a long time for the changes in the ocean to show up temperature-wise, because in addition to it heating up slowly, a lot of it is being hidden from us. But when we take temperature measurements at those bottom layers, they're getting warmer. And there's only one possible way they could be getting warmer, and that's warmer surface temperatures driving this conveyor belt. In addition, that carbon dioxide that I talked about before that's being dissolved in water to form carbonic acid, that's also being taken down to the bottom of the ocean. So right now the oceans are acting as a carbon sink. So the amount of carbon in the atmosphere isn't as high as you would expect by the amount that we're putting in, because there's a lot of it that's being taken out. But that carbon sink isn't infinite. It can't last forever. And even if we change the amount of carbon we're putting in the atmosphere now, that stuff's coming back around. So we cannot just sit and wait until things get bad enough and then we can stop. It's not like you can just hold your hand close to the fire until it starts to hurt and then pull your hand away. The fire's sticking around. You're going to continue to get burned. The other thing that's happening is that glaciers are melting. Now, glaciers are ice on the tops of mountains or in Antarctica on land. Water that's frozen is expanded. It floats because it expands when it freezes. When it melts, it shrinks. The volume is less. So an iceberg floating around in the ocean, when it melts, it doesn't raise sea level. It might actually lower it a teeny tiny bit. But water in glaciers and on the continents, that's like just pouring a glass into the ocean. It raises the level. As glaciers melt, fresh water comes into the ocean. In the North Atlantic, making the water fresher will make it less likely to sink because it's less dense. And increasing glacial melt could actually shut off that ocean conveyor system. If that happens, the poles are going to get a lot colder because the heat that is being transmitted from the tropics will be shut off, and the tropics will get hotter because there's nothing taking away that excess heat. In the 1300s, we went through what's called the Little Ice Age, and the thinking is that happened because a huge amount of water was released from North America following the last glaciation, and it shut down this ocean conveyor system and plunged Europe into an ice age, mini ice age. You've seen all the pictures of the canals in Holland with the windmills, and the canals are frozen and you can ice skate on the canals. Yeah, that doesn't happen now. Holland now is famous for growing tulips, not for ice skating. So what happens to global climate? Well, you would have colder, extended winters for much of North America and Western Europe. That's why I say we shouldn't call it global warming, because here it's not necessarily going to get hotter. It could get a lot cooler and drier, which means things that normally grow here won't be able to grow here anymore. But you would also expect to see drier, hotter climates for the southwest region of the United States. So we should be concerned if we ever see anything like that. I mean, if you have droughts in Arizona and New Mexico, or California that last for decades. 14 years and counting for California, aren't we? We're seeing this stuff now. So what if global warming isn't real? We hear this all the time, right? There are people who are what we call climate change deniers. Are there people who are making reasonable arguments about the science, saying it's not going to change 4 degrees, it's only going to change 3, or it's not going to take 50 years, it's going to take 100? Sure. But there's a huge difference between disagreeing about how much the change is going to be versus whether there's going to be a change or not. How many watched the baseball game last night? Red Sox. Woo! Did they win?
Yeah.
Can we argue about whether they won or not? No. Can we argue about why they won? Turn on sports talk radio, that's what they're doing. But the difference between arguing about why and how much is very, very different from arguing the if. The conversation needs to be about why it's happening, how much it's going to happen, and what we can do about it. Because the if is established. We're past that point. There is no dispute that carbon dioxide levels are rising. This is the graph of carbon dioxide levels as measured from the top of Mauna Loa in Hawaii. In the 1950s, about 315 parts per million. By 2005, it was 385. 2 years ago, I was there in Hawaii. It had nothing to do with this discovery, but we passed 400 for the first time ever. And you can just measure it. Nobody's disputing that. So there's no argument that carbon dioxide levels are in fact rising. The question is, what does that mean? And I've already told you one thing it means: ocean acidification. Carbon dioxide gets dissolved in the water, forms carbonic acid, and what that does is it dissolves things like coral, but also shells of things like diatoms and foraminiferans, the little tiny organisms that are the base of the ocean food chain. And those things are largely photosynthetic. They're the primary source of atmospheric oxygen. Is anybody still holding their breath from earlier? No, because you know that having oxygen is important. That's a problem if those things can't make or maintain their shells, because then they won't survive. They won't be food for other critters, but they also won't be fixing sunlight into food or releasing oxygen. And that has nothing to do with temperature. That's just the carbon dioxide. Here are little things called zooxanthellae. They are bacteria that live in the tissues of corals. Corals have this interesting behavior. They're animals, so they have to eat to survive. But they allow these zooxanthellae to live inside their tissues. And inside their tissues, the zooxanthellae perform photosynthesis. And the corals benefit from the food that the bacteria produce. The zooxanthellae get the waste products from the coral polyps, and that's fertilizer for them. This is called symbiosis. Both of them benefit. Zooxanthellae are very happy during the daytime. There's lots of sunlight, there's lots of food. Corals need oxygen. They breathe like you do. So do zooxanthellae. So do plants. The thing about plants is, during the day, there's enough sunlight where the amount of oxygen they use is less than the amount of oxygen they produce through photosynthesis. Same thing is true for zooxanthellae. So at night, the zooxanthellae aren't doing photosynthesis, but they're consuming oxygen. It's a little touch and go. But they're in the tropics. The sun's going to come up tomorrow, and they'll be happy. unless there's not enough oxygen in the water, because these things aren't breathing air. They're breathing oxygen by extracting it from the oceans. Oxygen is a dissolved gas, and dissolved gas concentrations are dependent on temperature. The warmer it gets, the less oxygen there is in the water. So one of the things we expect to see as sea surface temperatures increase is less dissolved oxygen and more of this. Normal healthy coral, which has color because of the zooxanthellae, can't get enough oxygen from the zooxanthellae during the day, and they're competing with them at night, so they kick them out. They expel them. And when that happens, the coral bleaches, turns white. Now, if it's a temporary thing, it's just a really hot day and tomorrow things are back to normal, the zooxanthellae can infect the coral and everything will be fine. But that's not usually what happens. What usually happens is the corals die. And then you get large stretches of coral reefs that are bleached out, dead. One of the things that ought to happen, if this whole global climate change thing is real, is we should see more coral bleaching. And we're talking about science here. So we have a model. We think it gets warmer, these bad things are going to happen. So those are predictions. We should watch and see if those things start happening. Because when they do, that's more evidence that we're right. So we're going to keep a really close eye on coral reefs to see if bleaching events start increasing in frequency. They have. They've been increasing in frequency for about 15 years now. In some places, like Hawaii, they're actually doing experiments at the Hawaii Institute of Marine Biology where they're taking warm tropical corals and transplanting them to Hawaii, which is colder because the corals in Hawaii can't handle the higher temperatures. So when people say there's no evidence for global warming, yes there is. And it's happening more and more and more often. So the predictions of our models tell us certain things should happen. Well, where's the evidence? What should we see if there is in fact a problem? We should see higher sea surface temperatures. Raise your hand if you think that's already happening. If your hand's in the air, you're right. We should have more severe storms. Check. We should have displacement of motile species. Motile means they can move. So animals that can't handle the heat should get out of Dodge when it gets too hot and go someplace else. Is that happening? Yes, it is. We should see more coral bleaching. Check. We should see deformed shells. Here's the temperature graph. This is called the temperature anomaly graph. So they take the average temperature from 1940 to 1980 and then plot how the current temperatures look compared to that. If it's red, then it's hotter than that average. If it's bluish, then it's colder than that average. What do you see pretty much everywhere across the globe? It's red. And if I got the more recent graph, it's redder. Not only are things hotter than they've been before, the rate at which it's increasing is increasing. How many tropical storms are we having? Well, the blue line is all tropical storms. It's increasing. Hurricanes are increasing. Major hurricanes are increasing. These are the things you'd expect. And the worst part about all these predictions is that the expectation isn't that they're going to get worse. It's that they're going to get worse faster. That the rate of things changing is supposed to accelerate. Displacement of motile species. Sorry, fish. But this is where you would find silver hake from 68 to 80, 81 to 94, and now. What's happening? They're moving to the north. Same thing with red hake. Same thing with spotted hake. They are all migrating up the eastern seaboard to cooler waters because that's what they're adapted to. But there's a problem with that. You might think, oh, that's fine. We didn't have that fish before. In a couple of years, we can fish for them. But those fish live on other things. If those other things aren't motile, they can't move. So these fish may very well migrate themselves right out of their ecological niche, where the food supply, the breeding grounds, all the things that they need aren't there. That's one of the consequences we're already seeing with increasing temperatures. Here are, this is 2 years old now, incidents of coral bleaching. Red dots are high, yellow dots are medium, blue is low, green is no bleaching. I want you to look very closely and see how hard it is to find green. Coral bleaching is not the normal condition. Coral bleaching indicates a sick reef, and those things are happening more and more and more often, even in the middle of the ocean. How could you have increased temperatures in the middle of the ocean? The only way that can happen is increased sea surface temperatures, and it's happening. We should start to see the deformed shells of forams and diatoms. We are. This is a newly formed shell. They produce this shell right after they change from a larval form. They produce a huge amount of energy to generate the shell quickly, and then that shell is maintained for the rest of their lives. This is what a new shell looks like. This is what they're starting to look like 15, 30, 45 days later. They are just dissolving away in the acidic oceans. Those animals can't survive under those conditions, and they feed everything. We should see higher sea levels. Here's a graph that shows the average from 1993 to 2017, average sea level. If it's blue, it's higher than the average. If it's red, it's lower than the average. What do you see? Sea levels are rising. Why is that a problem? Well, what happens the next time a hurricane comes ashore? You've all heard about the storm surge, right? Sometimes the storm surge is bad, but not really all that bad because it didn't quite breach the seawall. But you raise sea level a couple of inches and suddenly didn't get over the seawall is 5 miles inshore, especially on really shallow slopes, like in the Carolinas or Florida. Well, why is sea level rising? Well, part of it is the melting of land ice. You're just dumping more water into the bucket that is the ocean. But the other thing is what's called thermal expansion. Water, because of its unusual property, is weird for a liquid. Things normally get smaller as they get colder. Water does that too. It takes up less and less volume as it gets colder until it hits a certain point, 4 degrees Celsius. And after that it expands until it freezes into ice. That's why ice floats. So initially melting ice in the oceans will lower sea level, but as soon as it passes 4 degrees, it starts to expand again. Now water doesn't expand a lot. Look at this, we're talking about 1,000 cubic centimeters to 1,001 cubic centimeters. That's not a lot of expansion, but there's a lot of water. So even if all of the water only expands a little bit, that's a huge volume change. And that is going to drive up sea levels. And all of that then feeds back into this, what's called thermohaline circulation, the ocean conveyor belt. All of that stuff is all interconnected. And we're all interconnected. The problem that we're facing is a global problem. Is it a problem of our making? Did I do this? Did you do this? Remember what I just said about water. Doesn't have to expand much for it to have an impact because there's so much of it. Isn't that the same thing that we could say about people? There are 7 billion people on the planet. Okay. Imagine if everyone on the planet produced 1 cubic yard of carbon dioxide less than they do now. We're down 7 billion cubic yards. That's not insignificant. On the other hand, what if everybody produces 1 more? Now we've jumped it up by 7 billion. There is that multiplication factor that makes this such a problem. When the United States refused to sign the Kyoto Accords, it was a huge problem. But the reason the United States gave for not doing that is that developing nations like India and China weren't restricted in their ability to produce carbon. And they had the largest populations in the world and the fastest industrializing populations in the world. Now we could quibble about whether that's a good argument or not, but at least the facts on the ground are that that's true. But those countries have now signed carbon restriction agreements. And we haven't. I think there are only two left, us and Liberia. And I'm not so certain about Liberia. We're the one country in the whole world that's doing this. La 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 la, can't hear you. How embarrassing is that? With all of the things that we have going on in the world, the one thing that is going to affect directly everybody on the planet, we won't even acknowledge exists. Go to the EPA website where they can't even talk about climate change anymore. All the stuff that used to be on the EPA website about that, gone. Because we have a government, regardless of party, that just does this. La la la. We're not listening. We don't see a problem. We're not going to do anything. Where can that change? Every one of you. When you vote, is this what you vote about? Or is it something else? Is it, I don't want to pay as much in taxes, or I want this particular perk from the government, or I want this, or I want that? Does this factor into your consideration at all? Is there a political party that you can point to and say, that one, they're always on the right side of the environmental issues? Is there such a thing? Would you know it if you saw it? I wouldn't. I look, but I don't see anything that's a clear plan for dealing with this kind of stuff. So, I hate to break it to you all, but the grown-ups dropped the ball. Again. It's your turn. We're clearly not going to fix this. You guys are going to have it. So, it's now just a little bit after 12 on a lovely fall day in New England, and I bummed everyone in the room out. So let me leave you with something a little bit more uplifting, assuming that the sound is working.
The ocean. From above, a simple blanket of water. But below, a complex world full of color, life, and wonder. This is the coral reef, a timeless thing of beauty for all to enjoy. And yet, mankind's actions have destroyed over 1/4 of the world's reefs.
Please join me as we explore the fatal beauty of nature's underwater world. I will be your guide and your host. I'm Jean-Michel Cousteau.
Coral, growing only a few centimeters a year, has taken millions of years to build the limestone skeleton of the reef. And though located in nutrient-poor waters, the coral has learned to thrive. But it hasn't done it alone. It has developed an amazing relationship with algae, a tiny plant that lives inside the coral's body. This connection is delicate, and the introduction of additional nutrients can upset this balance, leaving the reef at risk. Little fish, I'm trying to make a documentary film.
A film? A film? I've always wanted to be in a film.
I was just explaining the delicate balance between coral and the algae living within its body.
Algae living inside the coral's body. Come on, that's creepy.
No, it isn't.
Yes, it is.
Isn't.
Whatever.
No, it is not a whatever. It's true.
How do you know? Are you a coral?
I'm Jean-Michel Cousteau. And I've studied the ocean all my life.
I'm Dory, and I practically live in the ocean.
Good for you. But now I must continue to make my film. So long, Dory.
Hey!
Anemones also share a delicate connection with their inhabitants, the clownfish.
Clownfish? Did somebody say clownfish?
What now?
Carlin, Burrito, this is... sorry, what was your name again?
I'm Jean-Michel Cousteau. Arrêtez la musique! I was trying to talk about anemones.
That's perfect because this here is Mr. Anemone.
Well, I don't know about that.
Yeah, Dad, you know everything about anemone.
Come on.
Oh. Anemones are really like snails, except no, snails is not, no. Oh, they're like a bed of stinging hair. Yes, a large bed of, no. Oh, imagine if spaghetti could talk.
That's enough! If we remain silent, we may see the chameleon of the reef, the amazing cuttlefish.
Did you want to see him change color? I can help. I can speak cuttlefish.
Qu'est-ce qu'elle fait?
Can you please change color for us?
No.
There's Carrie. Hey, Carrie. Rodrigo. Myron. My man, Myron. Bermuda. Hey, Enid. Yolanda. Phyllis. Gary. Hey, Gary.
Ça suffit! I'm trying to make a film here. Even the lovely Spanish dancer depends
Did
on...
someone say dancing? Clear the reef, Papa's back in town!
Whoa!
Stop! Let me talk. The ocean where you live evaporates to form clouds. The clouds produce snow. The snow melts, feeding rivers, irrigation, drinking water, then down drains through sewers, all back to the sea. Everyone, everywhere affects the ocean.
Wow, amazing.
Finally, you're listening.
Yeah, I can hear the ocean.
Ah, arrêtez maintenant, je ne peux pas travailler comme ça.
Mr. Cousteau? Jean-Michel? Are you there?
Where'd he go?
I'm back, and I am fine.
Can we get you something? Do you want a glass of water?
Dad, why is that coral white?
Well, you know when you get sick, you turn a little pale? Well, that's what coral does. It turns white.
What happened to it?
Well, as more humans use more energy, it creates more pollution. The result in global warming increases the temperature of the ocean. When this happens, the coral cannot survive.
Will it be okay?
Well, Nemo, it won't be easy. People must learn to live in better balance with nature, conserving energy, recycling, reducing pollution. But if we do all this, the ocean's temperature may lower, allowing the coral to flourish. In fact, tonight is the one magic night of the year when healthy corals reproduce. There, it is happening. Ooh.
Oh,
Ooh, look at that.
Whoa!
Amazing.
look at this.
Happy birthday, coral. Happy birthday. Happy birthday. Happy birthday. Happy birthday.
Incredibly, the corals release their eggs in a single night, so that even the hungriest fish cannot eat them all.
What's it doing? Dad!
When you're a little older, son.
As mankind's actions continue to damage and threaten the reef, we must take responsibility and change our behavior to protect and preserve it. For we are as connected to the planet as the corals are to the algae living within them. And just as it is...
Algae living inside coral? That's creepy.
No, it is not.
Yeah, it is.
Isn't.
It
Isn't.
is.
No, it's normal. See, they work together.
That's-
Algae are plants that make food for the coral, and corals fertilize the algae.
But when there's pollution, the coral can't get enough food from the algae.
Look!
Wow, you guys know a lot about the reef.
Well, it's not hard. You just have to pay attention and listen.
Then why won't you listen to me?
Oh, hi. Who are you?
I am Jean-Michel Cousteau! Upstage by fish. This would have never happened to Papa. Goodbye. I am Jean-Michel Cousteau.
Keep exploring the reef with Jean-Michel Cousteau at oceanfutures.org.
All right. Does anybody have any questions? No questions. When the ocean is dead, what happens to us? Huge population crash. We will not be able to sustain the 7 plus billion people we have on the planet, significant portions of the planet get their primary source of protein from harvesting things from the ocean. So if those ocean food webs collapse, that's going to be cut off. So what will we do? Well, we'll probably do the thing people are best at. Fight. There will be wars for scarce resources. Kind of what pretty much all wars are about. There'll be less food, there'll be less fresh water, there'll be less habitable land. It's going to get ugly.
So once the corals are bleached, even when they're reproducing, the ones that are bleached are not, they have no way to be like saved or.
Right. When you look at a coral reef, what you're mostly seeing is the hard shell that the polyps produce around themselves. So when the corals die, all that's left behind is that coral skeleton. Now, new coral polyps could settle on that and start to build anew, but once that happens, once they bleach, the coral starts to break down. And if it's acidic, they break down faster and those crumble. Reefs grow really, really slowly. And so even a small amount of damage could be 100, 200 years worth of growth. If you ever go snorkeling or scuba diving, don't touch the reef. Because when you do, you kill the coral. And if you break it off, I've seen people accidentally kick over a head of coral that's 500, 600 years old. And that's it, it's gone.
And I know that coral is made out of calcium carbonate. So I have horrible heartburn. Do they get like the material for Tums from coral?
Probably not. But those small shelly creatures, the foraminifera, the diatoms, things like that, when they die, their shells sink to the bottom of the ocean and accumulate in huge layers, which eventually gets pressed down and lithified and turned into things like limestone. So most of the calcium carbonate you use in that kind of stuff is mined from ancient seabeds. But that's another problem. Those ancient seabeds are calcium carbonate, which has carbon dioxide in it, which was taken out of the early atmosphere. When we dig that stuff up, we release that carbon dioxide back into the atmosphere. That's essentially what we're doing with fossil fuels. When you dig up oil or natural gas from under the ground, that's carbon dioxide that has been taken out of circulation millions, maybe hundreds of millions of years ago. When we burn it, puts all that stuff right back in the atmosphere. That's why carbon dioxide levels in the atmosphere are rising. We've got the system out of equilibrium because we're just dumping all the stuff from storage back into the atmosphere.
So where would the Tums come from?
From limestone beds, you can just mine this stuff. Other questions? All right, well, thank you all for coming. I hope you enjoyed the sustainability fair.